Welcome to topic 11. Oh, errors don't just pop up randomly. They happen for a reason. Our goal here is to now tie everything we've been talking about all along, different machine elements, bearings, actuators, and how do you design them all into a system so they all work together. What we're going to be doing is we're going to be looking at an entire machine, but the machine doesn't exist yet. The machine exists only in our brains as a structural loop. Some tool, workpiece, and something that connects it all. And our job is to fill in the bearings, the structure, the actuators, so it all works together to give you the required accuracy of motion that you desire. We're going to be doing that philosophically by assuming that the machine is not a collection of rigid elements, but every element has a little bit of wiggle in it. So when everything's wiggling a little bit, how's the sum total performance going to happen between the tool and the workpiece? That's the goal, is to be able to predict all this. And it happens for reasons. You have to use some statistics to do it, and we have some spreadsheet tools to help out with that. An error budget is just like a financial budget or a time budget. It's a low-cost tool that lets you very quickly estimate how good your thinking of a machine is. Once you can frame out the machine and rationally pick spacing between bearings, types of bearings, what the structure may look like, you can always then hit it up with more detailed analysis, but it gives you the starting point. The key thing we'll use for building the error budget is, as we showed just a minute ago, an image of the structural loop, which means that you may have several of those images, in which case you're going to construct several copies of the error budget for your different concepts, and that'll help you decide which is the concept you actually want to move forward with. We do that by just making stick figures of the machine. We initially don't want to put any sort of implied meaning behind sizes of things until we rationally pick what they are. To do this, we'll use an error budget spreadsheet, we call it, which is based on the mathematics of homogeneous transformation matrices, which you'll see allows us to start with a complex machine and just look at one piece at a time. Forget about the rest of the machine. You just do one joint at a time. And then how you actually model what are called the error motions of catalog items like bearings. Because the catalog items will not necessarily give you all the information you need in order to use the spreadsheets. So our design strategy will be the following. In a machine, there are four primary types of errors. There's geometric errors. That's when things move. They're just not the right shape you thought. There's load-induced errors when you put weight on things. Oof, it sags according to where the weight is on the machine. There's thermal errors. Things get hot and they expand, or they get cold and contract. And there's process-induced errors. When you're cutting, there's interaction between the tool and the workpiece that the tools deflect. There's surface finish issues. The material is compressed by the cutting force and it pops back afterwards. There are these four basic types of errors. During our concept phase, we're going to focus on geometric errors, and you'll see in a minute how we actually can design an entire machine just looking at the geometric-based errors. We're going to do that by apportioning the different amounts of error to the total allowable for the machine, such that then if you design for the geometric errors, you then will have a starting basis to accommodate the other types of errors. The error budgets are only useful for predicting accuracy and repeatability of a machine, depending on which types of error inputs you define. They're good for also good for predicting misalignment loads on bearings, because you can use them to, say, model, I'm going to have these two bearings are aligned by this amount delta. And remember from our previous lecture, if you know the delta and the stiffness of the bearing, you can get the force on the bearing, which you then use for your load life calculations. So our first stop is the structural loop. Structural loop, remember, is the path the force takes as it goes from an input to an output. So just, this is the tool, this is the workpiece. They come together, the tool operates on the workpiece, and this is the path the stress takes. The rest of the machine frame doesn't feel anything. If this is the tool and this is the workpiece, and you push together, then you can feel the flow of force all the way through it. You draw the structural loop such that it passes through every major compliance zone. Where you have here, for example, you can see 4 bearings, it's passing through the center of stiffness of the bearings. When you have not yet designed the machine, what you do have is an idea of the work volume of the machine. So you can draw that as a cube, and then using St. Venet's principle, be thinking about, well, how much outside of the cube do I have to be in order to contain an assortment of bearings that will be able to move through the motions of the cube. Consider these 2 configurations of machines here as an example of what you can do with a structural loop, purely in the concept thinking phase. 2 different types of grinding machines, surface grinders. Here's the part which would move in and out of the board. On the top machine, the vertical axis, the y-axis, is the column. The z-axis moves in and out. So if this is the spindle, where the tip here is the grinding wheel, it moves in and out, as does in the lower machine. But a very, very, very subtle difference between the 2. On the top machine, the bearing rail is fixed, and the z-axis would move along the rails like this. Excuse me for only moving one of the bearing rails. On the bottom machine, it's flipped. The carriages are attached, so the z-axis moves up and down, or the y-axis that moves up and down, and the z-axis moves in and out. So you see in the upper machine, as the z-axis moves back and forth, the bearing carriages, which are attached to that axis, and then here's the wheel, these carriages move forward with that axis. There's this much cantilever then between the center of stiffness of the bearing and the wheel. What that means is, as shown by the 2 structural loops here, in the backward all the way in position, this is the structural loop. When the part slides forward, or excuse me, the z-axis slides forward, you actually have the same shape structural loop in the forward position. The shape of the structural loop here does not change as the machine moves. That would tell me that the stiffness between the tool and the workpiece has a good chance of being the same regardless of where the tool is on the workpiece. If the stiffness is the same as I move, then the cutting forces will be producing the same type of deflection as I move. Remember, F equals kx. So philosophically, this type of machine can be used to cut with heavy cutting loads and still have an even part without any taper. In the lower machine, there's a position where when the grinding wheel is back because the z-axis is retracted, I have a real tight structural loop, very stiff. So if I'm grinding here, I have very high stiffness. So for example, grinding a very hard ceramic. When the z-axis extends forward across the part, the structural loop changes shape, and it's going to be bigger, and hence the machine is less stiff. And if I had the same high force here, I'm going to have more deflection, and I'll grind a taper in the part. That doesn't mean that this machine is better than this machine. It depends what you're using the machine for. This machine would make a better production machine where I have to rapidly produce large dies, for example. This, for example, is a better tool room machine where I can take the time to grind as the z-axis moves back and forth to what is called spark out, which means there are no forces on the tool anymore. And it also means I have a position in this machine where it's really, really, really super stiff for the highest of high precision grinding small, hard ceramic parts, which this upper machine would have more of a trouble dealing with. So it's all about what you want your machine to do And as you're envisioning what you want your machine to do, starting to sketch out possible structural loops to accommodate the motions you want to have happen. What I like to do is I like to look at machines and look at their work volumes and imagine the axes in the different positions in my brain, sketch out where are the centers of stiffness of the bearings, where are the centers of stiffness of the structure, what does the structural loop look like for that machine. So I learn a lot just by looking through the magazines at pictures of machines or going to trade shows and imagining what does the structural loop look like in there. So preload your brain with what other people have done in the past. So when I refer to doing a concept sketch using stick figures, remember this from topic 3. So when you're laying out your machine, for example, here are 3 versions of a machine. This is a bridge type machine. This is a cantilever machine where I've got the cantilever it's driven on one axis, so this bridge that reaches out does have the option of bending back and forth, which it shouldn't, right? Whereas the bridge machine, both sides of the there's 2 x-axes, a master and a follower, that drive both sides of the bridge. Here the bridge is only driven by one side, and then this is a totally cantilevered machine. 3 very different machines to achieve the same type of motion of a workspace of about 2 meters by 3 meters. So it depends upon what you're trying to do. But here you are, you can sketch it out with stick figures. You could run the error analysis to see can your machine, which of these concepts meet the required accuracy of the machine. You don't want to put any more detail than this initially, so you as a designer are not encumbered by some implied size structure from a solid model, for example. Keep your options open. And the purpose of the analysis then will be to enable you to think rationally with these open options. So here's how I actually begin when I have to design a machine. And this is a version of a spreadsheet that I will bring up here in a minute. It's called the Axis Error Apportionment Estimator. What this does is it says, okay, customer says, I want 3 axes of motion. And you know what? In the end, I need the tool to be accurate to the workpiece or repeatable to the workpiece. You just have to know which you're dealing with, repeatability or accuracy. But we'll stick with accuracy for now, of 10 micrometers. Now, I haven't said the size of the machine. I don't need to know any more information than that to start, because what I'm going to do is I'm going to go through and say, okay, good. Now, I'm not going to rush right off and say, oh, I need to use air bearings or roller bearings or whatever. I want to rationally have a hunting license to pick out what hardware elements that I'm aware of in their performance areas am I likely to be able to use. And this is what we'll do with this spreadsheet. It's going to start with the number of axes, the total allowable error, and I've got these 4 sources of error that we talked about earlier. I have a factor F, which gives each of them equal importance. So if I made this number bigger than that one, all I have to do is put in the relative importance. Then it will apportion how much error goes to each one. So if they're all equal importance, each one of these factors gets 2.5 microns of error, for example, here. And then because it's 3 axes, each axis gets 1/3 of that. Now you may say, whoa, that's not right, because the axis near the tool tip, it's a little bit of motion axis, and it's a lot easier for it to get this 0.8 microns than an axis that's way far away. Well, you could go through and reapportion this in accordance to that thinking, but now you'd be implying which axis is located where. And in the very early design stage, you don't want to do that because you don't know where the axes are yet. You can always go back and modify if you so choose. And then an axis, remember, is going to have bearings, support structure, actuator, sensors, and even cables. So for very high-speed machines, very high precision, the load of cables can even be important in terms of the accuracy of the machine. The sensors may be not a big issue because you're designing a low accuracy machine, and low accuracy being tens of microns, and it's easy to get micron level sensors because remember, you always have this kind of curve in the back of your head of cost versus performance, looking something like this. And if your machine is in a performance level zone here, and this is what the curve for sensors looks like, well, it's going to be easy to get what you need, so you would downgrade this, and the sensors and maybe only get 0.2 of the total error. And the same thing if it's a beefy machine, and I'm not worried about cables pulling on it, this may also be downgraded by 0.2. And we're going to walk through the spreadsheet a little bit here in a minute to see what we're doing with this, how this affects the numbers. So you see what I'm going to do is I'm going to build a map of the types of performance levels I'm going to need from the different components in order that for all the axes together, when they work together to yield the total allowable error. So I have a good chance of succeeding in my machine design. Okay, so I'm going to clear out of here and bring up the spreadsheet a minute to show you a little more detail.